This is question 18 from the second CSAT sample paper. Here we're asked how many squares can be made on an n by n grid, and this is including tilted squares, so not just vertical ones, but ones at all angles. So if you want to have a go at this question yourself, pause the video now. Okay, so to do this with upright squares, so where the sides are vertical or horizontal, isn't too difficult. But when you have to deal with all the possible angles, it gets trickier. I think the easiest way to show this, it's hard to see with small grids. So the natural way to do this is to start with very small grids and start working up. But then when you get to, say, 4x4 and especially 5x5, you start to see that the method you used for small grids might not work for larger ones because of all the different tilted squares you can get. So let's start with 5x5, and I'm not going to show all the different squares, just make it clear how many different tilted squares there can be, and why we have to take the approach, why I think we have to take the approach I take. Okay, so here's a 5x5 grid, and vertical squares we can do, for instance, like this, side length 1, or I could do one with side length 2. Or I could have one big one which has side length 4, like this. I won't draw the other sides. So I could have one like that. I could have a bunch of these small ones, slightly smaller number of these medium-sized ones. How many tilted squares can I have? Well, the first place to look naturally is this kind of thing, which is tilted at 45 degrees. So you might do all the vertical ones first, then you start doing all these ones at 45 degrees. But the problem is you can have quite a few angles as n increases in size. So, in particular, one tilted square we could have is like this. So, I'm basically going along 4 and down 1 each time. So, it might not look square because of my slightly wonky grid, but because I'm always going, so here I go up 1, along 3, sorry, not 4, and here I go along 1, down 3, so all these sides have to be the same length by Pythagoras. So there's going to be at least one of those, and that should be 2 of those. How else can I do a tilted grid? Well, I could do, for instance, I can join this to this, so go up 1 and along 2, and then I go along 1 and down 2, and I go down 1 and along 2, then I do this. So there'll be at least one of those, but actually you can see there'll be multiple of those. And the angles these sides make with the vertical are different. So we're basically going to have to consider these cases all separately if we do all the squares at one angle together. So it's not a good way of thinking about it to just count how many there are for, say, 4x4, then go up to 5x5 and imagine there's going to be a simple relationship between them, because when you increase the grid size by 1, you increase the number of angles you can tilt your squares at, and you get a lot more tilted squares as n increases. So we need a very systematic way of addressing all these tilted squares. So what I will do is do the vertical squares first, so these ones with these ones aren't tilted first. You could do it as part of doing the tilted squares, but I think it's slightly easier to see first, and it makes the tilted case a bit more systematic. So we'll do these first, and then we'll go on to the tilted ones. Okay, so let's think about the vertical squares. I've drawn a clean 4x4 grid. The size doesn't really matter. So first of all, there's obviously one big square. What's the side length of that? It's going to be, if n is 4, it's going to be n minus 1, because there's 3 lengths along each of these. So there's going to be an n minus 1 sided square. That's going to be one of them. Now suppose we look at the next smallest kind of vertical square we can fit in. So with side length n minus 2. That's 2 by 2 here. So I could draw one up in the top left here, and once I've drawn that, I can shuffle it one to the right, or one down, or one to the right and one down, So basically I can shuffle it up or down by 1, this way by 1. So there's 2 positions it can be in horizontally, 2 vertically, so that means there's going to be 4 positions it can be in overall. And if we think about the next smallest, so here that's the smallest possible, but we'll go on. The next smallest is going to have sides n minus 3, and that means I can move it down, in this case 2 times, so I can fit it in 3 different positions vertically and 3 horizontally. So that means there's going to be 3 times 3, which is 9 lots of that. And in general, if I have an n minus k-sided square that can fit in, I get k squared of them, because I can move them up or down k minus 1 times, or left to right k minus 1 times. So there's basically k possible choices for the height, k for the width. So it gives us k squared of these. You don't necessarily have to think about it that way, you could just do this for increasing grids and see the pattern. How big can k be is I've written that k can be anything up to n minus 1. So if k is equal to n minus 1, then I have a 1 by 1 sided square, which is the smallest possible. So what value does that give me for the number of these vertical squares? Well, just adding all these squares up. So I'm doing 1 squared plus 2 squared, etc., all the way up to n minus 1 squared. And in the question they actually give us a hint. They give us the sum of k squared and the sum of k cubed from k equals 1 to k equals n. So this is where we're using the k squared part. And they give us a formula. The formula is the sum from 1 to n of k squared is a sixth times n plus 1 times 2n plus 1. But here, instead of n on top, I've got n minus 1. So this is going to be n minus 1. This is going to be n. This is going to be 2 times n minus 1, that's 2n minus 2, plus 1 is 2n minus 1. So the answer I get at the end is a sixth n minus 1, 2n minus 1. So that's for the vertical squares. So now we'll have a look at the tilted squares. So here I've drawn a tilted square, and bear in mind the corners are going to be on a grid, an n by n grid. And therefore the distance, the vertical distance from this point to the next point has to be a whole number, and so does the horizontal distance. And because it's a square, this distance a here, so calling a the vertical distance and b the horizontal, this here has to be a, this has to be b, and so on all the way around. And remember, when we were dealing with the vertical squares on a grid, it mattered how many times we could fit them in. So basically what mattered was the width. So when we had a square that was 1 unit wide, and so we had a 4 by 4 grid, we could fit it in 3 times horizontally and 3 times vertically, and that gave us 9 times overall. And we're looking for a similar thing here. We're looking for how many times we can fit this tilted square in. And what matters here is the total width, a plus b. So this here is b, this distance is going to be a, so this total width is a plus b, likewise this total height is going to be a plus b. So we just need to be able to fit in all the corners, and as long as a plus b is less than or equal to n minus 1, which is the width of the grid, we can fit this in. If it's strictly less than that, then the difference is how many times we can move it over, or move it up or down, and still stay in the grid. So we've got total width a plus b. How many times does it fit in? Well, when we had a vertical square of length k, it fitted in n minus k squared times. Likewise, this is going to fit in n minus a plus b all squared times. Because imagine I try to fit this into an n by n grid, how much space is left to the right here? And that's going to be n minus a plus b, and I can move it over that many times to keep it in. Or move it up or down that many times, and then I square it to get the total number of squares. So this depends on a and b, but this gives me a way of counting the number of squares of every tilt. So the numbers a and b determine the tilt. Bear in mind, if I called this b, if this was b and this was a instead, then I'd have basically the same, I'd have a very similar square, it would be the same size, but it would be the other way round. It would be like it was reflected, and those count separately. So basically if we swap a and b, we get a completely different square. So how big can a plus b be? Well, it has to be less than or equal to n minus 1. And we want to count through a and b as far as possible, so we need to figure out how big they can be. So a, bear in mind a and b both have to be at least 1. So a can be anything between 1 and n minus 2. And then what can b be? Well, b has to be at least 1, and it could be anything up to n minus 1 minus a, because this just says b is less than or equal to n minus 1 minus a. So if we can pick a as any value between these 2 points, and then we can pick b as any value between these 2 points, and those will give us a different tilted square, and then we'll get a different number here for the number of those squares. And I've just made a note here that, for instance, if I chose a as 1 and b as 2, or a as 2 and b as 1, those give me different squares, so those count separately. So I'm not worried about double counting. Okay, so now suppose we look at all the possible values a can take and think about how many tilted squares there can be in total. So if a is 1, b can be anything between 1 and n minus 2, because a plus b has to be at most n minus 1. And if, suppose, say b is 1, then remember the number of those tilted squares is going to be, because a plus b is 2, it's going to be n minus 2 squared. If b is 2, we're going to have n minus 3 squared. We can have everything down to 3 squared, 2 squared, 1 squared. So if a is 1, this is the total number of tilted squares we can have for all the different values of b. If a is 2, what's it going to be? Well, it's going to be, b can be everything now from 1 to n minus 3 instead. And therefore we're going to get the same sum, but we cut it off 1 earlier, because the size of b is more limited. And likewise, if a is 3, we're going to have the similar sum, but only going up to n minus 4 squared. So we can continue this forever. If a is n minus 3, then b has to be 1 or 2, and we get this. And if a is n minus 2, the only value we can have is b is 1, and a plus b is n minus 1, and we can only have one of those. So this is the number of tilted squares with a equals 1, this for a equals 2, etc., all the way down. So something that would take far too long would be to work out what this is. We can, because we've got a formula for this. We could work out what this is for a equals 1, and for a equals 2, and then for the general case a equals k, and then add all those together. But there is a trick to doing it more quickly, and that's to see a pattern in this. This is almost like a triangle, and what we can see here is we've got n minus 2 lots of 1, and then n minus 3 lots of 2 squared, and n minus 4 lots of 3 squared, etc., all the way up to 2 lots of n minus 3 squared and 1 lot of n minus 2 squared. So that means the total here is n minus 2 times 1 squared, plus n minus 3 times 2 squared, etc., all the way up to 2 times n minus 3 squared, plus 1 times n minus 2 squared. And what's the general term? The general term is k squared, so k is this, and then n minus 1 minus k is what we're multiplying it by. And we're doing this for every k between 1 and n minus 2. Why is this useful? Well, because now I can rearrange this sum to n minus 1 times the sum from 1 to n minus 2 of k squared. So let's take out this part and multiply by the k squared. And then we do minus k times k squared is minus k cubed in its own sum, because part of the hint they gave us was the sum for k cubed, as well as the sum for k squared. So now let's work out each of these terms. So when we plug in k squared into our formula, we have n minus 2 times n minus 2 plus 1. Then we've got 2 times n minus 2 plus 1, that gives us 2n minus 3, and then a sixth. I'll just put the n minus 1 in front still. And then for k cubed, it's a quarter times n minus 2 squared times n minus 2 plus 1 squared, which is n minus 2 squared, n minus 1 squared. Now again, we want to make this as quick as possible for ourselves. So the best way is to take out as many common factors as we can. So let's take all the fractions out, so we can take out a 12th. And also we've got 2 n minus 1 factors in each of these, and also 1 n minus 2 factor. So if we take those all out, we take out a 12th, n minus 1 squared, n minus 2. Then in here, because I took out a 12th, I now multiply by 2, and I've got 2 lots of 2n minus 3. Because I took out a 12th, I multiply this by 3, and I've got a spare factor of n minus 2. And now this term, what does this come to? We've got 4n minus 3, and it's just n, and then the numbers cancel. We've got minus 6 plus 6. So this just becomes n, and so my final answer for all the tilted squares is a 12th n, n minus 1 squared, n minus 2. So now we just have to add that to the number for the non-tilted squares, and we've got our final answer. Okay, so now I'm adding the two formulae already found. This was the one for the vertical squares, and this for the tilted squares. So again, we want to make this as quick as possible. So let's take out a factor of a 12th, and then we've got a factor of n and n minus 1 in both of these. So when we take that out, we've got 12th n, n minus 1, and then here, because I took out a 12th and multiplied by 2, so I've got 4n minus 2 from here. And here I took out a 12th n, n minus 1, so what's left is n minus 1 times n minus 2, which is n squared minus 3n plus 2. And then if I collect up here, the numbers cancel, so I just get, and the 4n and the minus 3n give n, so I just get n squared plus n, and that factorises to n, n plus 1. So I can take the n out to make it n squared, and n minus 1, n plus 1 is n squared minus 1. So I simplify this to a 12th n squared minus 1. And this is our final answer for the number of squares. I've tested this for everything from n equals 0, which could be a special case, but it actually works, up to n equals 5, and it gives the right answer each time. That actually gives you a slightly cheaty way of doing the question. Since in their hints they give you the sums for k squared and k cubed, and the k cubed one at least involves n to the 4, you can expect the answer is going to be a quartic in n. And that means if you work out the values for n equals 1 to n equals 4, well, okay, so a quartic, you have 5 unknowns. You have the coefficients of n to the 4, n cubed, n squared, n, and a number term. So you can either calculate just by looking at the grids the values for n equals 0, 1, 2, 3, 4, if you count 0, or you could do 1, 2, 3, 4, 5, but working out the number for the 5 by 5 grid is a bit more work. But those will give you, if you plug in those values of n, those will give you into your quartic with 5 unknowns. Those will give you 5 simultaneous equations with 5 unknowns. You can find all the coefficients of the quartic, and these turn out to be the only coefficients that work. So you could, just knowing what they expect you to do, you could actually find the quartic without understanding why this is true in general. But as I said, that's slightly cheaty, because it's not really taking the question on its own terms.